And so what we consider is the following. So we consider VO inside of Cn. So it's a germ of an isolated singularity of certain algebraic variety. So V is a fine algebraic variety, and O is an isolated singularity. Namely, so away from the origin, we don't have any singularity near the origin. Maybe there are some away from the origin, but okay. And then consider a small ball. So this is a ball of radius maybe epsilon around the origin. And then consider the intersection of them. So I consider intersection of this, and also consider intersection with the boundary of this. Okay. So maybe I denote it by L and call it a link of the isolated singularity VO. Then this L carries a natural contact structures. So L carries a contact structure as follows. So I consider the tangent bundle TL. It's a subbundle of tangent bundle V away from the origin, and then that one is considered as a subbundle of the tangent bundle of this complex vector space restricted to L. So this one is a subbundle of this thing, and then here we have complex multiplication. So this is just. And then consider intersection of this thing with this thing. So we have two subbundles in this ambient vector bundle, and then I denote this bundle by Xc, and then this Lxc is a contact manifold. So here I said that origin is an isolated singularity, but just the easiest case is the non-singular V, like a linear thing or something. So if I consider this Cn, sorry, no. If I consider just this thing, so this is a sphere. And then we can also consider the same thing. So T is 2n minus 1, intersection with J, T is 2n minus 1, inside of this T, Cn to this boundary. And so this one is actually a standard contact structure on the sphere. So this is the standard contact structure on these things. So this one is a kind of sub-object of these things. Okay. So here I consider this contact manifold, and then consider so-called symplectic fillings of this contact manifold. So let introduce a notion of symplectic fittings, and I don't know if this one is good or not. Okay, so let LC be a contact manifold, and then consider as a compact symplectic manifold which bounds L. So we consider compact symplectic manifold whose boundary is this L. And then we call this guy is a so-called symplectic fitting of this contact manifold if it satisfies certain compatibility relation between Xi and omega as follows. So we call this W omega. Maybe today I only consider so-called strong symplectic fittings of this thing if there exists a certain vector field around the boundary. So if there is a vector field near the vector field on a color neighborhood of dW, which satisfies the two things. So one is that this omega actually dilates this symplectic form like this. And the second condition is that X is outward normal along the boundary. So the picture is something like this. So you have certain contact manifold here, Y out of LC, and then I take certain compact symplectic manifold, and near the boundary, sorry, I need one more thing. I have some vector field which is like this. It's a normal vector field of the boundary which points outward. And sorry, I also need this. So, and also Ix of omega gives Xi. So, is the contact form for this Xi. Okay. So, if we have this vector field X, then we call this W omega a symplectic fitting of this contact manifold. So in this case, we have round sphere like dB epsilon 0, and then we just consider radial vector field like x naught is just a sum of xi ddxi plus yi ddyi, and then one can easily show that this actually dilates standard symplectic form. Maybe I need 1/2 or something, but I need 1/2 like this, equal to just this guy, and it's point outward along the boundary. And if I take interior product of this thing, so this thing is omega 0, then what we have is yi dxi minus xi dyi 1/2. I think this is correct, right? And if you take kernel of it, then you get standard contact structure on the sphere. So in this case, this x is given by this explicit one. Okay. So even though we have singularity at the origin, what we are considering is link, which is away from singularity. So therefore, we can think of such objects. Yeah. So okay. So from now on, I consider only complex surface singularity and want to tell you something about it. Okay. So we consider isolated surface singularity. And first, I just want to refer some result on this symplectic fittings. Okay. So examples. So there is a class so-called simple singularities. Sometimes it is also called as rational double points, or Duval singularities, or Kleinian singularity, or ADE singularities. But anyway, they are the same thing. And I just want to give you equation or something. Okay, so we have two ways to define this. So first, we consider, first way is just consider the following thing. So take finite subgroup of SU2 and then consider quotient of complex plane by this gamma, and then you have origin as an isolated singularity. Okay, so this is one way to understand this. And such gammas are classified by linking diagrams. So there are type AN, DN, and EN. Sorry, E6, E7, E8. So such gammas are classified, and so corresponding singularity we also call AN type singularity, DN type singularity, and so on. Okay, so this is one way to understand this. But a particular feature of this singularity is that they are also realized as so-called hypersurface singularities. So in fact, we can embed it into C3. And then these singularities are defined by the following defining polynomials. So here we consider x n plus 1, x to n plus 1, y square, and z square. And here x square y plus y n minus 1 and z square. And the other one is x to the fourth y cube and z square, and x cube y cube and z square, and x fifth y cube and z square. Okay. So there. Are those global, or is that just the singularity? Yeah, I just consider germ of singularity at this moment. Yeah. But no. In this embedding actually global, because this is really special feature of these singularities, so-called it's a weighted homogeneous singularities. So therefore, if you have something in the neighborhood origin, you use the homogeneity, weighted homogeneity to extend everything. So therefore, this is actually global, also global. And we can also consider finite subgroup of U2. So this is, I don't know, finite quotient singularity. It corresponds to gamma in U2. We also have some sort of classification, not only this, but other things. And among them, some special thing is so-called cyclic quotient singularities. So there is also some subclass is cyclic quotient singularity. Okay, so I have simple singularity, and then it's a kind of slight extension of this. And then we have also so-called simple elliptic singularities. This one I will tell you definition a little later, but there are some special example for this. Wait. Maybe better to look at something from here. Okay. So there are some simple elliptic singularities which are obtained as hypersurface singularities. So like x cube, x6, y cube, z square plus lambda xyz, and x fourth. In fact, this explicit form doesn't really play so much role in our argument, but just for just making things a little bit more explicit, I just want to present these things. Okay, and xy plus z square plus w square. Okay, something like this. So these three, I should write defining equation, so therefore I should write these are equal to 0. So this is defining equation of three variables. So it gives us hypersurface in C3, so therefore two-dimensional object. And here also we have xyz space, and then consider hypersurface there. This also. This one we have xyzw, so it's four variables. So we have four-dimensional space, and then we take these two independent polynomials and then cut out certain surface. Yeah? This of 4 minus 2 is 2, so therefore this of surface. So they are hypersurface singularities, and this one is so-called complete intersection singularity. Okay. And certainly there are much more complicated singularities, but I just stop here because for these things somehow I can tell you about simplex fittings. Beyond this, actually our understanding is not really complete, and we are not really satisfied. So for this simple singularity case, actually maybe some terminology I have to explain later, but for simple singularities, I should mention his name. So all my talk today is a joint work with Hiroshi Ota. And we actually classified all simplex deformation types of this. So we determined, so any minimal, I have to explain what minimal is. Minimal strong, maybe in this case it's not necessary. So symplectic fitting are symplectic deformation equivalent to so-called Milnor fiber. What is Milnor fiber? If you have this polynomial, and then these singularities are defined as a zero set of these polynomials. And if you set this one is equal to non-zero number, say 1, and then in this case we have smooth hypersurface, non-singular hypersurface. So we call them Milnor fiber. Just take this polynomial and set it into equal to 1, and then we call it Milnor fiber. And for finite quotient singularity, actually in the cyclic quotient case, actually this was already classified by Paul Riska, and he has classification of symplectic fittings, minimal symplectic fittings. And for other finite subgroup, this is a joint work with Mohan Bhupal, and we also have kind of classification of this. Why I put these things? Because we have kind of list, and which covers all the symplectic fittings. But maybe we may have 2 or 3 in the list, which eventually gives us the same symplectic fittings. So it is we have a complete list, but some of them may give us the same thing. So therefore this quotation mark here. And finally, for simple elliptic singularities, again this is joint work with order. Sorry. This is simple singularity case. Sorry. This is simple singularity case, and this is simple elliptic singularity case. In this case, minimal symplectic fitting. I should add this strong here. Minimal strong symplectic fittings are anything symplectic deformation equivalent to either to so-called minimal resolution of the singularity, or to so-called smoothing. So this smoothing is a kind of generalization of this Milnor fiber. So I wrote some equations, and for them we have somehow good understanding. Certainly there may be still some problem remain, but we can describe all the possible symplectic fittings. Okay. In this case we have only finite many types. And one of the observations I want to say is that in general we have infinite many of them. And certainly, it may be folklore that there are infinite many of them for general singularities. But that is one thing I want to say. And the other thing I want to say is that, so here we have these polynomials, and this one, x to the 5th y cubed plus z square, gives us famous Poincare homologous sphere. And here we have also 2, 3, 6. It is not a homologous sphere, but we have this 2, 3, 6. But we consider the next thing like 2, 3, 7. And then 2, 3, 7 is no longer in this list. So we want to understand what it is. And then so far I cannot really say so precisely what is the simplex filling, what are possible simplex fillings for the singularity x to the 7th plus y cubed plus z squared is equal to 0. But still we have something. So yes.
So do they all come from algebraic information?
In this thing, probably yes. I have to check, but I think yeah for them I think so, yeah. And these guys I have to check. And this thing I also.
Sorry, for elliptic singularities, is true?
Elliptic singularities probably I don't know. I mean, what I'm saying is that they all come from algebraic geometry. But yeah, okay. So one more thing is that this one actually tells us the following. So maybe I have to tell you what the elliptic singularity is. So VO is called simple elliptic singularity if its minimal resolution, so-called if its minimal resolution have exceptional divisor which is just one elliptic curve. So this one origin is a isolated singularity, and then pi is a proper holomorphic map, and pi is proper holomorphic map, so that pi is biholomorphic away from the origin. So that means v tilde minus pi inverse 0 to v minus 0. It is biholomorphic. And so this is the resolution. And then we call this thing a simple elliptic singularity if this pi inverse 0 is nothing but one elliptic curve. Just topologically one torus. And then you have an embedded torus inside of surface. And then topologically there are several types, namely the Euler number of the normal bundle. In other words, self-intersection number of these things. So degree of symplectic simple elliptic singularity is defined to be maybe minus of self-intersection numbers. And then for them, actually degrees are given as follows. Maybe this one is 1, 2, 3, 4. I see. So this one, so here I write degree. Degree is 1, 2, 3, 4. And degree can be arbitrary positive integers. Because there is a theorem which says that if you have configuration of curves whose intersection matrix is negative definite, then you can contract them to isolated singularity. So therefore, in particular, if you have an elliptic curve and then take a normal, you take a holomorphic line band over there with given self-intersection number, and then you can actually contract the zero section to be a singularity. So therefore, here degree can be arbitrary. And this one says the following. So if you have simple elliptic singularity of degree k, if such a thing appears as a hypersurface singularity, then degree must be 1, 2, 3, and this type. If it is realized as complete intersection singularity, then 1, 2, 4. Nothing else. And then I have to, so this is resolution sense. And now I have to say a little bit about the smoothing. So what is smoothing? So smoothing is a...
So topologically, V tilde is just a neighborhood of a
Yes. So now I just to talk about smoothing. So if you have a family, like maybe, so B is maybe just a curve, complex curve, and then consider certain variety which somehow fiber over this. And there is one point here, and over P we have this original V. So we have singularity VO. And then if there is a family of variety over some curve, and at one point this is exactly given one. And if as a point, if the inverse image is non-singular, then we call such a thing as smoothing. So V is singular object, but you have a family of variety, and then if you perturb, and then you get some certain non-singular object. Then we call this guy as smoothing. So smoothing is not unique, and this definition requires a little bit more, like a flatness of the morphism or something. But I just want to say this. So you can deform to a smoothing. You can deform if you can deform it to a non-singular object, then we call it smoothing. And for them, actually, smoothing. So for simple elliptic singularities, if it admits smoothing, then degree must be 1 to 9, nothing more. And such a thing we can also observe from our result. So we classify all the things, and then these two things appears, certain thing only appears up to 9. And after that, we only have this type. So only this after degree 9. So if degree is bigger than 9, then only this, no smoothing. But this one, so this in this case degree is between 9 and 1. Okay.
So is the converse true? Does the curve degree less than not always have a smoothing?
I think so, yeah. Our proof doesn't really give such a thing. But it's a result by Pinkham. So, and these things are actually due to Kyoji Saito. And then this result is due to Pinkham. I have to explain, sorry. So I only explained the symplectic feeling so far. Now I have to explain this. So I want to keep this thing a little bit. So it's a but A, D, E6, E7, E8. Okay. So we call for anything is okay. So W omega is a symplectic form manifold. Either compact or closed. So it's called minimal if W doesn't contain symplectically embedded two sphere of self-intersection number -1. So in algebraic setup, minimality is equivalent to the non-existence of -1 curve. So this is just symplectic analog of it. And if we have such a thing, and then we can blow down, even in symplectic categories. Okay. So, okay. 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 And we have following small observation, which is something like this. Where is it? No, notice. I don't know where it is. Yeah. So one more thing is the following. So one more thing. It is really a small thing, which is not really an extension of this, but yeah, some observation. This also joined with him. So let's consider Riemann surface of genus D. So here we consider elliptic curves of genus 0 case. But here we consider surface of genus G, so called Riemann surface. Genus G. And then consider certain S1 bundle over here. So this is a circle bundle with first Chern number n, which is negative. And then if you have circle bundle with non-vanishing, with C1 n, which is negative, then we can cook up some connection here. So pick a connection on this thing, so that curvature is equal to some multiple of area form. So maybe n times the area form. Okay, so this is a negative number. And then this gives us certainly contact form. So this C is a contact structure. Sorry, so this is just digression. So this is digression. So for sigma g, we consider for each negative integer such as circle bundle, and then this circle bundle carries certain contact structure. And then for this contact structure, we can say the following. Yes. So if this number n is smaller than 2 minus 2g, then the intersection form of intersection form of any strong symplectic filling of this thing is has no positive eigenvalues, has no positive part. So intersection form is the bilinear form, symmetric bilinear form. And so over maybe rational numbers, you can diagonalize it. Over real number, you can diagonalize it, and then you have positive part, null part, and negative part. So this statement says that intersection form has no positive part. So this is not so satisfactory, but still we can say something about this. And in this case, actually, certainly.
Before you erase that, I guess symplectic deformation equivalent just means a one-parameter family of symplectic forms, right?
Yes.
And on the boundary?
On the boundary, always convexity conditions.
So okay, but not necessarily fixed, but kind of.
Yeah. So it can be yes.
So it remains strong filling through the.
Yeah. So we have this. Then as a result, with Ota says that if this n is more negative, then we can say a little bit more. So one of the results with him is that if this number is if this number is less than minus 4g plus 4, then we have more information. Namely, our symplectic filling W can be compactified to a irrational rule surface, rule symplectic four manifold. So this is just analog of rule surface in algebraic geometry, and this pi, so the thing pi inverse of 0 inside of W is mapped to the 0 section. Is a section of this. Corresponds to a section of. So rule surface is a P1 bundle over sigma G. So first we can compactify this W to such a P1 bundle over sigma G, and then we have a 0 section here. This is of this thing, and this one is actually mapped to 0 section of P1 bundle. So then somehow original thing can be understood as a complement of a section in irrational rule surface. Okay, so therefore, if this one is so negative, then we have better understanding. But up to here, in this range, actually, we can only have this. And then one of the small things which I want to state is the following. So if this number is not so negative, then we have infinite many minimal symplectic fillings. So that is one thing I want to say. So, okay. So I consider this y ng sigma g, and if this n is between 0 and 2 minus 2g. So here 2 minus 2g, here I also here. Okay, then there exists infinite many distinct symplectic fillings, strong minimal symplectic fillings. Of this thing. So in this case, we have this result. So it has no positive part. But here, in fact, the positive part can be arbitrarily large. So B2 plus of this filling W can be arbitrarily large. So in particular, it doesn't satisfy this property. So up to 2 minus 2g, after 2 minus 2g, we have this result. But between these two ranges, we have only this. We have infinite many of them. So this is one thing I want to say.
What do you mean by arbitrarily large? For a fixed n and g? Or?
No. So for given thing, fix n and g, then we have a sequence of minimal simplex fittings. If you consider B2 plus can be arbitrarily large.
For fixed n and g?
Yeah, for fix this.
What is W?
W is simplex fitting, sorry. So I have to say that B2 plus, maybe I have a sequence of strong string fittings, and this one diverges to infinity. Okay, so another result I want to mention is the following. Here, I consider these special kind of polynomials. And now I want to consider 2, 3, 7 case. And this is still, it is not so satisfactory, but I can tell you something. Where is it?
I want to talk about a little bit about the relation between these different feelings.
Relation between
What is the relation between these different feelings? How do you construct it?
this one.
Yeah.
So maybe I can explain how to construct this. It's rather easy observation. Maybe some of you maybe already know this, like Honda-san, or maybe David already knows this, right? But for this, I see 237. Yeah. Okay. So now I want to consider some sort of polynomial like f p q r x y z. So this is a polynomial of 3 variables of Fermat type like x p y q and g r. So if you consider this sort of things, and then there are 3 classes of these polynomials. So one type is p, the inverse of sum of inverse of them is bigger than 1 or equal to 1 and less than 1. So we have this quantity is quite crucial in the theory of singularities, and we have here we have some A, D, E type things. Okay, so this corresponds to simple singularities of type AN, and I think D4, E6, E6, E7, E8. Such a thing appear in this story, and here we have simply elliptic singularity, and the degree must be this 1, 2, 3, right? Degree 1, 2, 3. So these things belong to these kind of special class. So here, if you just consider all the possibility of PQR, and then
Less than one swap somewhere.
pardon? Opposite. This is sorry. Thank you very much. So this one allow you to have only finite many PQR, and if you list them up, then actually you get this. And in this case, if you consider this thing 2, 3, 6 or 2, 4, 4, 3, 3, 3, you get exactly 1. In general, we have this situation. So far, what I talk about is mainly these classes. And now we want to also know a little bit about this case. And so today I take this thing, and then want to say quite small observation. So it is not really so satisfactory, and I don't know how much we can say in future, but what we can do is the following. So the theorem, it again with the order, and let X be a minimal symplectic filling of singularity x square y cube and g to the power 7th is equal to 0. And then we have the following inequality. Assume that B2 plus of this guy is non-zero. So in particular, it is not a minimal resolution of the singularity. And then 3 times signature plus 2 times the Euler number, topological Euler number, is bigger than or equal to the case of Milnor fiber. So this is Milnor fiber. So maybe I have to write it 2 times chi top of V2C. Okay, and this is in fact more explicitly it is equal to 2. So here V237 is just a Milnor fiber, so x square y cube and g to the power 7 is equal to, let's say 1. Okay, it's a Milnor fiber. So we don't have so nice thing, but somehow it may say that among such minimal symplectic fillings, maybe the Milnor fiber is kind of, I don't know, canonical or something. I don't know. So one more question is that you may have lots of fillings, and then one may find sort of best filling or something. And sometimes Milnor fiber gives you best one, in some sense, but we don't know so well. So I just stopped saying this. So
this particular combination representing
this thing, as if you know a little bit about the Seiberg-Witten theory, this one is equal to C1 square of something. So always this combination appears so often. So C1 square of something, if you use the Hilbert-Freeman law, Hilbert signature theorem, and just C2 is equal to Euler class, and then you get this. And C1 square is related to the dimension of the modular space of monopoles. Okay, so this is what I want to say. So this one and this one. So how much time I have?
5 minutes.
5 minutes. Then maybe I just pick this one. And this is so easy, but maybe I just explain. So it's so easy. So now I consider the following. So I have one curve. This is sigma g, and self-intersection number. First, we consider the case that self-intersection number is equal to 2 minus 2g. And then here, we already mentioned, if you consider some, if you consider disk bundle of this, and certainly you have, I don't know how to call it. So I consider the following thing. So let L be a complex line bundle of first Laplace equal to this 2 minus 2g. And then take its unit circle bundle. And then on this unit circle bundle, you get this. And if you put appropriate simplex structure here, and then this gives you filling of this guy. Now we consider a little bit smaller things like this. And it is really a special case because 2 minus 2g is Euler number of this guy. So if you consider the cotangent bundle of this, then if you take the unit circle bundle is diffeomorphic to this thing. But this is not only the thing I can say. So in fact, we have kind of symplectic cobordism. It's a symplectic cobordism between this and this. So here we consider contact structure coming from connections. And here we consider Xi as a unit circle, unit cotangent bundle. So this is unit cotangent. So because it's unit cotangent, so you have standard contact structure. And then maybe it was first noticed by Macduff, and later Geiges and Mitsumatsu cook up more easier form. But anyway, you have certain, actually it's a product. So here is certain y, omega. So that this side you have this y and g with Xi contact connection, and here you have this unit circle bundle of T star sigma g coming from this unit cotangent things. And then, in fact, it is a simplex filling of these two. So this is convex. This is also convex. And so you remove smaller tubular neighborhood of this, smaller tubular neighborhood, and glue in this. And then originally we have something like this. This is a boundary y. And inside we have boundary of this unit cotangent bundle. So it has both convex ends. And now we want to find some concave filling of this. And actually we can cook up a lot of ways, cook up infinite many of them in many ways. So then there exist infinite many distinct concave filling of this thing, and just glue in there. And then you have different things. I mean, in particular, B2 plus can be arbitrarily large. So therefore, you have infinite many of them. So this is the case to the self-intersection number is 2 minus 2g. If it is between 2 minus 2g and 0, then you just make a blow up. And then you can achieve this self-intersection number and then do this. So more generally, if you have a maybe cycle of certain curves, and if such a thing appear as an exceptional divisor of the resolution, and if you assume certain condition on the intersection number of them, then after smoothing we come to this. So often we can. So this is not only the case we can handle. There are some other cases more complicated, but this is a way to get this. And for this one, maybe I have no time, so maybe I stop here. And thank you very much.
Any questions?
So now you reduce my